So, today's lecture is going to be about the KMT, the kinetic molecular theory, and the gas laws. I want to briefly go over the KMT. We have these 5 postulates that we just quizzed on, and I want to make sure that we're on the same track with this. The first one is that particles are small. Particles of gases are tiny. Okay. Then they're so tiny that the distance between the molecules is great. Okay, and this is where we lead to the idea of volume. Okay, that it is really the distances between the molecules that enable gases to occupy volume rather than the size of the molecules themselves. Okay, the third one was that these molecules collide with the walls of their container. They're in constant random motion. Okay, their constant random motion. Their constant random motion leads to collisions with the walls of their containers, and those collisions lead to pressure. This is the pressure definition of the KMT. Okay, the fourth one is that molecules do not attract or repel each other. I can call it do not exert forces. In fact, they do not exert intermolecular forces on each other. Okay, so if you remember the like van der Waals forces or hydrogen bonding or that sort of thing, or if you remember that we talked about walking past somebody in the mall and they smell nice and you kind of drift over a little bit, and that doesn't happen with gas particles. Okay, that there is no. Now, it really does. It really does happen. But for purposes of us studying our gases, they're moving too fast for those effects to actually happen. So, molecules do not exert intermolecular forces on each other. And finally, number 5 is moving molecules have kinetic energy. Okay. The average kinetic energy is proportional to the absolute temperature of the gas, and this would be the temperature to the average temperature of the gas, and this would be the temperature part of the KMT. And this also leads us to the absolute temperature also is the Kelvin part. Okay, so when we talk about absolute temperature, we're talking about Kelvin. And one of the things that we must do when we're dealing with our KMT and we're talking about our gas laws and our temperatures is we must be our temperatures must be measured in Kelvin, because our Kelvin temperature is the only one of our scales that has a lowest temperature at 0. Okay, the other ones go negative, and when you're doing things with proportions and they cross into a negative range, you don't have you lose your proportionality. It doesn't work. So those are the KMT, and we're going to use those, and we're going to start with numbers 2 and 3. Where we have pressure versus volume. Okay, pressure versus volume. So, we are going to start with Actually, before we do that, I'm going to show you guys an animation I made because I'm cool like that. Yes, yes, yes. Okay, thank you. All right. Let me get to my library here and... Okay, so here's my animation. Yes, I made this, like, from scratch. You need to pass? Okay, and so I want you guys, for right now, just take a couple minutes and think to yourself, what really is going on here? Okay, think in terms of particles. Okay, in terms of particles and collisions and motion of particles. Okay, so if I told you that this right here, this is called a piston, by the way. So this moving top to the container is called a piston. And if this is my independent variable, if this is the variable, perhaps I don't use black on a black background. If this is my independent variable and I push down on here, what am I changing? I'm changing the volume of the container, right? But if we have the same number of particles, it doesn't help getting a text from my parents while I'm recording a lecture. I'm sure you know how that feels. Okay, so if you decrease the volume, okay, the number of particles is still there, right? The number of particles doesn't change. Are they moving faster? Okay, but the distance between them gets less. But the distance between them gets less because I am changing the volume, right? Okay, so me changing the volume forces all these particles into a smaller space. But then what occurs more often? The collisions with each other and the walls of the container. So what we're doing is, by decreasing the volume, we're increasing our collisions with the container. And this is a pressure versus volume relationship. That is the volume decreases, the pressure increases. Okay, and as it releases again, as the volume, okay, squeezes and then it comes back out again. Stop. Okay, as the volume moves out again, your spaces are wide and there are fewer collisions with the walls of its container. Yeah? I wish there was a sound component so I could record a little sound every single time that my atoms hit the walls of the container, but nope, not yet, not to be. So what do we have here? We have this piston here. And if our piston depresses, we'll call this 2 liters. And we'll say that this is a pressure of 2 atmospheres. All right, I'm just establishing a starting point. We have a pressure of 2 atmospheres. This is twice atmospheric pressure in a container that contains 2 liters of gas. And we cause our container to, right, yeah. You can see, even just by drawing the same number of molecules in there, that they're closer together. On average, the spaces between them are closer together, so we had to decrease the volume. But if we cut the volume in half, no, half of 2 is not 2. Half of 2 is 1 liter. What do you think the pressure is going to be? Okay, because remember, if we decrease the volume, what happens to our collisions? There will be more of them. to the point where it is proportional. So if we cut our volume in half, our pressure should increase proportionally. So it should be 4 atm, yeah? Okay. What if I allowed it to expand again, and I'm going to need a bigger, we're going to need a bigger boat. Okay, you can even see here that the average space between the molecules is significantly larger here. That if my volume in this one is 4 liters, what do you think the pressure is going to be here? That if we compare it to this one, if we double the volume, we're going to cut this in half, right? So our pressure would be 1 atm. All right, this leads us to a graph. Aha. Okay, that this is a definite mathematical relationship, and it leads to this graph. I will. Okay, and it leads to, as I like to say, the most awesomest graph ever in the history of evers. The hyperbola. Okay, it is the hyperbola. Why is it the greatest graph in history? Because that is hyperbole to describe the hyperbola. Okay. So this relationship is that our pressure times our volume. In this particular case, if we multiply our pressure and our volume here, what's this going to be? It's going to be 4. How about here? How about here? 4, right? Pressure times our volume. 4 times 1 is 4. 4 times 1 is 4. 2 times 2 is 4. Okay. All of these will plot onto this graph. Or if I had drawn them correctly, it would have plotted onto this graph. But this is the general shape. And that our pressure times volume equals a constant, some value. In this particular case, it would be 4 liter atmospheres. All right, that's what we established here. But that leads us to this equation. And now, mind you, this is called, then, this relationship is called an inversely it is inversely proportional if we have, this is our volume, and this is our pressure, although those are relatively interchangeable. Okay, so this is the inversely proportional relationship, and that gives us situation where if this is situation 1, this is situation 2, and this is situation 3, that P1 times V1 is going to equal this constant. But that same constant is also equal to our pressure from our second one plus our volume times our second one, from our second one, which is still going to equal our third situation, P3 times V3. All of these are going to be equal to each other. And this brings us to Boyle's law. Boyle's law, where P1 V1 will equal P2 V2, and this is the practical version of it, that if you have a gas, that everything else stays the same. You have the same temperature and you have the same number of molecules. When you multiply the pressure and the volume, it will stay constant. Or the product of the pressure and the volume that you have in one situation will equal the product and volume that you have in the second situation. And that leads to this one goes up, the other one goes down relationship. Yeah, so as our volume increases, our pressure decreases, right? Okay, or as our volume decreases, pressure increases. Okay, I do want you to write over on the side. There are 2 conditions that must be met in order for this to be true. N, which is our number of molecules, and T, must be constant. The number of molecules. In other words, this has to happen at the same temperature, and you can't change the amount of gas you have in the container. You can't let any gas out. You can't put any more gas in. If you close the container and then manipulate it, this is what can happen. Okay? All right, so that is Boyle's law. Now we have our next relationship. I do not have a nifty animation for you for this one. Sorry. I know. It's just because I don't care. Okay. Now we have this one, volume and temperature. So, we have our container. And on our container, we have a mass that is pushing down. So it's a force, it's a weight that's pushing down our container. Right now, our temperature is 200 Kelvin, and our volume is 2 liters. Okay. Now, what do you think is going to happen to all of our molecules in our container what will happen to the molecules in our container if we light a fire under it? What's that? What starts moving faster? I don't know what a gas is. Tell me about the particles. The molecules start to move rapidly. How do you know that? That if I heat it up, what am I adding to our system here? Okay, I'm adding heat, and heat is a form of what? Heat is a form of energy. So if I am adding energy to our container here, what happens to our molecules? What increases? And according to our term, what does? The kinetic energy. Okay, because we are adding to our kinetic energy, but all of the molecules are staying the same, right? We're not changing molecules. Okay, that means the mass of each molecule stays the same. What has to increase? Before that. Okay, it's what is it? If we're increasing the kinetic energy, that means what is affected of the molecules? They're moving faster. Okay, now, if they begin to move faster, okay, but our pressure stays the same. In other words, we have to maintain the number of collisions with the walls, the number and the force of the collisions with the walls. So remember, we'll establish our constants here. This is volume and temperature that we're looking for a relationship for. Our number of molecules and our pressure are constant. So if we're looking to maintain our constant pressure, and we have the same number of molecules, when these things start going faster, the only way we can keep the same pressure is to do what? Is to allow our container to expand. And that's what balloons do. Well, no, I take that back. It's not what balloons... Well, they can, but that's not how you blow up a balloon. But that's a non sequitur. We'll get back to that. So if we increase the heat, then all of a sudden, okay, that's a little weight on top of it. And now we have our same molecules. They're moving faster. Pew, pew, pew. Pew, pew. Pew, pew. Pew, and pew. All right, where these all have shorter lines, right? Okay, they all have shorter lines. So, The way you draw this, by the way, is that longer lines imply more speed. If there's more speed to the molecules, they're going to be hitting the walls of the container more frequently. But if you allow the container to expand to maintain the same pressure of the collisions, okay, now you have the volume versus temperature relationship. And if I doubled my temperature here, in fact, if my temperature didn't double, if we allowed the temperature to increase to 300 Kelvin, okay, if we allow our temperature to increase to 300 Kelvin, what do you think our volume is going to change to, Joseph? That is showing that we're maintaining the same pressure on the container. Okay, we're still on the piston, and if we have this weight on top, it's the same force for over the area. What do you think our new volume would be if we increase our temperature from 200 to 300? It would be 3 liters. Okay, same thing would happen the other direction, that if we put, if we put ice cubes, and I'm drawing some really crappy ice cubes. If we put our gas into an ice bath, okay, our volume is going to decrease. In fact, if we drop our temperature to 100 Kelvin, that's really cold. Considering that would be negative 170 Celsius. What would our volume be? It would go from 2 liters down to 1 liter. Okay, so you guys might see that there's a progression here. We have a relationship between these. That gives us another graph. Our graph, in this particular case, looks like that. That's our temperature. That's our volume. And volume over temperature equals a new constant. This is called directly proportional. Okay, this is a directly proportional relationship. We could have written this a different way, and this might look better to you as being a directly proportional. We could have written this as V equals KT, and K would represent your slope of this line. Okay. Okay. This relationship gives us our volume. So we have 1, 2, and 3 over here. Okay. Oh, it's one of those days. Yeah, okay. That the volume in our first situation divided by our temperature in our first situation, okay, is this constant, which is going to equal our volume over here divided by our temperature in the second situation, which will equal V3 over T3. And if you look at it, this is 1 over 100. This is 2 over 200, which reduces to 1 over 100. This is 3 over 300, which reduces to 1 over 100, right? So this proportion stays the same across the board. All right, this is called Charles' law. And I don't want to get into grammar arguments here, but I like putting the apostrophe S on a proper name that is singular, yet ends with an S. Okay, I was schooled during second period today when they objected to that, and they showed me that grammarians are also accepting the other version. So, well, it didn't say that mine was wrong, it just says that the other is also accepted, which is abhorrent to me, but we will accept it. Okay, so now we have these two laws. We have Boyle's law and Charles' law. We have Boyle's law that gives us gives us P1V1 equals P2V2. And we have Charles' law that gives us V1 over T1 equals V2 over T2. This leads us to what is called the combined gas law. This is the combined gas law, not to be confused with the ideal gas law, which we'll be talking about tomorrow. The combined gas law is by taking both of these together. Okay, and as long as, okay, so the assumption okay, it assumes that our number of moles doesn't change, that the number of molecules, we're not increasing or decreasing the amount of gas. We're just taking a gas and we're applying new conditions to it. That P1 V1 over T1 equals P2 V2 over T2. And so it maintains the inverse proportionality of P and V, and it adds the direct proportionality of V over T, and it combines them into one equation. You use this equation. Okay, this is a change. This is a change equation. In other words, when you have a gas that has before and after characteristics, when you're reading a problem, or you're dealing with a gas that has one situation before, and you want to find out what it's going to be like after you make some changes to it, you're going to use the combined gas law, as long as it's the same gas. Okay, we will incorporate our number of moles tomorrow when we talk about the ideal gas law, but today we just have the combined gas law. Okay, and so you would be able to take you would have 5 of these variables, and you'd have to, you could find the sixth, find the one that you don't have. This comes into play, in particular, with the idea of STP. Because now you need to know what STP is, and you pretty much need to memorize it. Standard temperature and pressure dictates 2 of our conditions, whether it's before or after, whether you start with STP or you finish with STP. Temperature is equal to 273 Kelvin, and it is equal to 1 atmosphere. Oh. These are your standard temperatures and pressures. Now, I'm going to recommend that you deal with these first because they're easiest. You have to do Kelvin, and 1 atmosphere is 1 atmosphere, and it's easy to deal with. There are other versions of this. 273 Kelvin also equals 0 degrees Celsius, and it equals 32 degrees Fahrenheit. Both of these are considered STP, but regardless of that fact, when you're doing these, you have to work in Kelvin. For pressure, I give you a whole bunch of different versions of the standard pressure. 760 millimeters of mercury. We have 101.5 kilopascals. And there's another one, and I think it's 1010 bars. Or millibars, sorry. Millibars, or 1.01 bar. And this is a much more rarely used, and I'm not going to expect you to do it. 1010 millibar. MBAR. Okay, so when you get into your combined gas law and you start trying to solve these problems, these are the ones that you're going to want to use. Now, the pressures, as long as you keep your units the same, the pressure you can use any unit of pressure for combined gas law. You have to use Kelvin whenever you do a calculation that requires temperature. Okay, and that's it.